Alright, hi guys. Now we're going to talk about Chapter 7, basically Section C, and we're going to talk about several things about how gravity can affect other objects, meaning which planets and satellites, moons, etc., and comets. So let's go ahead and finish the rest of the story. Now, what we have is how gravity affects planets, and we know that there's going to be competing competition between the planet and the sun. And what happens when the sun starts spinning, it was collecting its mass and getting bigger, bigger, and bigger. And our planet and the planets are collecting their own masses, some of them getting smaller. And what would happen is they would get closer to the sun, it would speed up, and they will come to a point where the velocity, transcendental velocity, matches the force that's being pulled by the sun, and it will stay in a particular orbital path, and basically all the dust in that path will get swept away and by the planet's gravitational pull, and they will get a little bit bigger, and then they start moving around a little bit until now they're pretty much constant. And that's how this gravity affects the planets. And what was interesting is that the stuff that laws dealing with planetary motion was developed in the 1700s by a fellow Newton, calling him a gentleman in Europe that lived around the time of Newton named Kepler. And I misspelled his name, but you get the point. And he had developed three laws. And the first one is that each planet circles the sun, in this case, or a star, in an elliptical orbit. And the sun is at one focal point. So an ellipsis is basically like an oval. And it may be a little narrow at one end, maybe not a pure oval, more like an egg shape, but it has two foci. And distance between the foci would dictate how circular or how elongated this orbit is. We know the Earth is not a full, let me draw a nose and a mouth. We know that the orbit of the planet is not purely circular. It is elliptical, but it's not whacked out. And so things we need to talk about these objects, an oval or elliptical orbit that we have two foci, 1 and 2, and this is a little far out. Actually, the focus for us is probably about here. The sun is at one end. There we go. There's a big sun, and the planet is kind of circling around. We have the vertex, minor axis, major axis, and a semi-minor axis is from the center to the edge. Full minor axis is the short end, going from the center to both sides, the short, and then the major is the longest part. And so the sun's here, the planet's rotating around, and you got the near end and the far end, and we see that in all the planets. I think the one that is not really pretty elliptical is Neptune and Mercury, if I believe that, if I remember correctly. Talk to Mr. Jarvis if you have any questions. So that's the first law. Second law, draw an imaginary line from the star to the planet. The area it sweeps out in two equal times will be equivalent. So if we look at this, we look at our planet and we say this delta time is about, let's say, 3 days. Delta T2 is 3 days. Then the area of 1 will equal the area of 2. That is something that Kepler theorized, and it is true to this day. So that's something we need to think about when we're looking at planetary orbits, and actually what NASA and the Air Force does, or the Space Force, when they're setting up satellites, is they go figure out what the orbitals are, where to send it to, and make sure that the time it takes to go from here to here, we send out the satellite here, make sure it goes right to meet our target at the same place and not anywhere else. So this is how engineers figure out where to send things in outer space. Now the third law is a simple proportionality, that t squared, the period, squared, the time it takes to go around the sun, square that, should be proportional to the average radius cubed. So if we know the periods of the planets, and that is related, and square that period, how they going around the sun, and take the cube root, we should find the average radius between that planet and the sun. And this is holding true for the most part. And so that's what we're looking at with Kepler's law. And what we're going to do with how gravity works is that the sun has a good pull on all the planets, and it does go elliptical. And what happens to this as the planet goes by the sun, it gets a little bit faster, and as it goes out towards the apex, past the sun, goes a little farther out, it slows down a bit, and then it comes back and speeds up. And this is how it's always doing this. And it's going to be set like this until something happens. So what we're going to do is that to make this an equal sign, we have to add a constant. So if we want to say t squared is equal to r cubed, we got to multiply a constant, I'm going to say k, that is constant for our planetary system or all systems. And scientists were trying to figure out what k is, and it's actually the universal gravitational constant. And I think times 2 pi. That's part of it. And so this is important to know, because we're going to go to a couple of equations that you're going to use in the problem sets. And one is going to say that the period of the orbit is equal to 2 pi times the square root of radius cubed over gravitational constant times the mass in the center of the object. And for most cases, this is going to be the sun. If we're looking at a satellite, it's going to be the mass of our planet. The mass of the object circling doesn't matter, because it's not being affected by the force of gravity. The force that it feels is only come from one place, and that's the center, the sun, or whatever's in the center of the orbit. So this is why we only have one mass, and that's the mass of our sun, or the middle, that's the focal point of our ellipse. And velocity, the orbital speed, is actually a little bit easier. That's the square root. Now remember, it's distance divided by time. So when we doing determining velocity, it's actually equal to gravitational moment times mass divided by r, and then you take the square root of that. Hopefully that will make a little bit of sense. And if you really want to think about it, take r squared out of this, so it'll be r times square root of r over gm, and rearrange it. So I can do this real quickly. So t is equal to 2 pi times the square root of r cubed over gm. If I take r squared out, so this will look like the square root of r squared times r over gm. I can take that and move that out, so it'll be t is equal to 2 pi times r over r times gm. Now, what the interesting thing is, if I move this to the multiply both sides by square root of gm over r, so square root of gm over r times t, that's equal to 2 pi r, divide both sides by t, This is the tangential that's the velocity of the object going in a circle. The distance, 2 pi r, is the circumference of a circle. So distance over time, the velocity, is equal to the square root of gm, gravitational constant times mass, over r. So that's where we get this. It's just a simple mathematics. And realizing we're looking at a near circular orbit, which is what most of our planets do. And that is end of the lecture for chapter 7. And you'll have a test over this. Have fun.